neurons are the unit of the nervous system. They're functional units, and these are just simplified diagrams. I mean, you know, and we have axon and dendrites, we have the cell body. They come in all shapes and sizes. The chemical and physical basis of cells, of neurons, leads to the structure of neurons. Okay, and also the function. And based on the molecular basis of cells and the chemistry of neurons, these that we've just described, that gives the neurons a unique functional property that no other type of cell has. It can generate and transmit action potentials. I mean, that is a fundamental principle in neuroscience. You have to know this, that the chemical and physical basis of cells underpins of neurons, underpins its ability to generate and transmit action potentials within the neuron and from one neuron to the next, which is basically transmitting, you know, firing, neurons firing. So we'll talk about that now. And in neural networks, that becomes important because that's how information is computed in networks of neurons. Okay, so that's the main message of this video that I want you to understand. Okay, these are some Nobel Prize winners that you can that have contributed a lot to our understanding of the mechanisms. Hodgkins, Huxley, Claude and Sackman and Carlson, Kandel. Kandel's the guy. He co-wrote the book Principles of Neuroscience, I think. Okay, so that's that. And so there you go. So the action potential. I'll be very brief here. So it's based on potentiation. Potential, which is in electrical potential and chemical potential, or electrochemical potentials, which is the differences across the membrane. So in that case, the transmembrane voltage differences that are based on electrochemical changes. And what we have is, you can see on the right here, we have a diagram that it's not a good diagram, but you can see the plus in the top neuron. That's a neuron, that's a cell body and an axon. You have the positive inside the axon that travels through the axon, and that is the action potential. The other thing is, you know, there's other information here. You know, do print out the PowerPoint and look up these, the Goldman equation, Nernst equation. You should know about these for university in the first year neuroscience. So we're going to talk about this now. So what we have is a ligand, a neurotransmitter, binds to a ligand-gated a receptor, and that opens an ion channel. There's depolarization, and that depolarization is carried through. Okay, that's the action potential, and that's based on the voltage-gated ion channels. So here, what we have is, look at that graph. You have to know that graph for A level. Okay, very simple. So you start at the resting potential, minus 70 millivolts. You get a stimulus, and then once it reaches a threshold, based on the movement of the ions, once it reaches a threshold, you get a massive depolarization in the membrane. That is when the sodium ions diffuse into the neuron, so it becomes more positive, so less negative. Then at the top point, the sodium gates close and the potassium gates open, and that's when the potassium goes out of the neuron, and that's the repolarization process. And then there's a hyperpolarization, a refractory period, during which you cannot have another action potential. You have to wait till the end, at the end here 6, you have to wait till you get back to the resting potential. That's important, and we'll look at why now. So there you go. This is these are ion channels, open and closed. So you get a stimulus input, and then if it reaches a threshold, it fires one action potential. And then if there's still a stimulus, again another action potential. 1 1. If it's not stimulating enough, 0. Okay, it's not a fraction. It's 0 or 1. 1 1 0 0 0 0, and then again 1 1 1 with the stimulus input. You cannot have in the bottom right here, so you have a 1, but you cannot have a 2. Okay, either the action potential fires with an amplitude of 1, which is an arbitrary unit of 1, or it doesn't fire at all. You can't have 2, a value of 2. You can't have value of 0.5. Okay, it either fires with value of 1 or it doesn't. You can't have 2, you can't have 0.5, you can't have a continuous, like the black block here. It cannot be. It fires once with value of 1, or it doesn't fire at all. It either fires or it doesn't fire. And with it fires with the same amplitude, but you don't get a continuous. It doesn't stay at the peak here. See, there's a quick depolarization and repolarization, and then there's a refractory period. You cannot have, with continuous stimulus, it goes 1, pause, 1, pause, 1. It's not just 1 continuously. Okay, I hope that makes sense. You have to know this. It's important. And the other thing is, okay, so that's it for that's what I'm going to say about action potentials. But we have a transmitter that binds to the receptor, there's depolarization, the action potential travels through the axon to the synaptic bulb, the end of the axon, at which point we have vesicle release of transmitters, and again that goes through the synaptic cleft, the gap between neurons, and then again same process happens in the other neuron. Action potential fires in the other neuron if there's enough stimulus input.